All right, welcome to this explainer. If you've got a midterm creeping up on units 1 and 2 of deep learning and neural networks, you know what? You are in exactly the right place. We are going to cut right through all the noise and give you the absolute conceptual clarity you need to go in and ace that exam. Seriously, even if you've missed every single class so far, stick with me. By the end of this speed run, you're going to be ready. So let's just dive right in.
Here's our survival roadmap for today. We're hitting Neural Networks 101, activation and loss functions, how neural networks learn, gradient descent and optimizers, conquering optimization challenges, and finally, a rapid exam revision. We're taking you step by step from the absolute basics of a single artificial neuron, all the way up to mastering those advanced optimization fixes.
Okay, Section 1, Neural Networks 101. Let's build our foundation right now with the fundamental building blocks of deep learning. Now, mark this down because this conceptual model is exam important. It elegantly mimics a biological brain. Just like a real brain uses synapses to connect neurons, an artificial neuron takes inputs, raw data, and multiplies them by weights. You can really just think of weights as a measure of importance for each input. Then it adds a bias to shift the baseline, which basically ensures the neuron can activate even when all your inputs are zero. Finally, it takes that entire mathematical sum and passes it through an activation function to get your output. If you see a short answer question on neuron components, just remember those four: inputs, weights, bias, and the activation function. So what happens when we actually start stacking these neurons together? Well, you get different architectures. First up, feed-forward neural networks, or FNNs. These are super simple. Data moves in exactly one direction, straight from input to output, with absolutely zero loops. Second, we have the multi-layer perceptron, or MLP. This introduces hidden layers between your input and output, and crucially, it uses backpropagation to train. Finally, the deep neural network, or DNN. Honestly, this is just an MLP on steroids. It stacks multiple hidden layers to extract incredibly complex patterns for heavy-duty tasks like computer vision or speech recognition. Moving right along to Section 2, activation and loss functions. These are the mathematical engines that allow our networks to solve complex, nonlinear problems instead of just, drawing straight, boring lines. Listen up, this one is absolutely exam important. Be ready to compare these exact functions. The sigmoid function converts inputs into a range between 0 and 1. It's super smooth and forms the backbone of logistic regression for binary classification. But it suffers heavily from the vanishing gradient problem. Basically, the learning signal gets so incredibly weak that the network simply stops learning. Tanh is a bit better because it outputs between -1 and 1, giving you a zero-centered alternative, but it still totally struggles with vanishing gradients. Then we have ReLU, rectified linear unit. ReLU just outputs the maximum of 0 or x. It's the absolute deep learning favorite right now because it computes significantly faster and drastically reduces that vanishing gradient problem. Now, you might be wondering, how does a network actually know if it's making good predictions? That's where your loss function comes in. If an exam question asks how a network measures its mistakes to guide the learning process, you define the loss function. Simply put, it measures the error between the actual output and the predicted output. For classification tasks, you're almost always going to use cross-entropy loss, which heavily penalizes incorrect predictions to essentially force the network to learn faster. Section 3. How neural networks learn. Let's actually look under the hood at the mechanics of how a network improves itself over time. You've got to memorize this exact 4-step sequence for your short answer questions. Honestly, think of it like taking a practice test. Step 1, forward propagation. The network takes a guess forward on the test. Step 2, error calculation. It checks that guess against the answer key using the loss function. Step 3, backpropagation. It looks backward through the network to see which weights, or which topics, it totally misunderstood. And Step 4, weight update. It adjusts its knowledge using a learning rate so it does better next time. That loop right there, that is the entire essence of machine learning. Here's another almost guaranteed exam comparison. How is the data actually presented to the network? Well, supervised learning acts like a teacher, providing exact answers. You give the network labeled input and output data, like explicitly marking emails as spam or not spam. Unsupervised learning, on the other hand, forces the network to find hidden structures completely on its own, using only raw input data. Think clustering customers by their shopping behavior. And just to round out the whole shebang, reinforcement learning is distinct from both. It relies entirely on a system of rewards and penalties, which you'll often see in robotics or game-playing AI. All right, leveling up to Section 4, gradient descent and optimizers. Optimization is just the algorithmic process of finding the best possible weights and biases to drive down our prediction error. When we talk about the gradient descent formula, your learning rate, represented by the Greek letter alpha, is literally the most critical dial you can turn. It dictates exactly how big of a step the algorithm takes down the error hill toward the minimum loss. If your learning rate is too small, your network is going to suffer from slow convergence. It'll just take forever to learn. But if it's too large, you get unstable overshooting. The network just bounces wildly around and never actually settles on the optimal solution. Another exam important highlight for you here, be prepared to contrast the different variations of gradient descent. Batch gradient descent uses the entire training dataset to calculate the gradient for one single step. This gives you a really smooth, stable optimization path, but man, it is computationally slow and massively memory heavy. Contrast that with stochastic gradient descent, or SGD. SGD updates the weights using just one training sample at a time. It's highly noisy and bounces around a lot, but it's super fast and requires very low memory. Because of these two extremes, we usually use mini-batch gradient descent. It uses small groups of samples, acting as the perfect, widely used Goldilocks compromise. But what happens if basic gradient descent just gets completely stuck in complex networks? Or what if it's just way too slow for today's massive datasets?
Well, you upgrade. When basic methods fail, you turn to advanced optimizers. RMS Prop adapts the learning rate dynamically for each parameter by dividing gradients by a moving average. But the real star of the show here is ADAM, Adaptive Moment Estimation. ADAM is the absolute gold standard in deep learning right now because it beautifully combines the dynamic learning rates of RMS Prop with momentum. Think of momentum like a snowball rolling down a hill. It builds up speed to just blast right past small, noisy bumps in the data. This combo gives you fast, efficient, and highly stable training, especially when you're dealing with giant datasets.
Section 5. Conquering Optimization Challenges. We're looking at the highly testable roadblocks your network is inevitably going to hit during training, and more importantly, exactly how to fix them. Exam important, for sure. You've absolutely got to know these two catastrophic failures. The vanishing gradient problem happens when gradients become so incredibly small during backpropagation that the early layers of your network just straight up stop learning. The updates shrink to basically nothing. This happens a lot if you use sigmoid activations in deep networks. Conversely, the exploding gradient problem is when gradients become massive, violently derailing your training with huge unstable updates and causing numerical overflow. So if you get an exam question asking how to escape flat plateaus, where the error hill is completely flat and gradients hit zero, or saddle points, which act like false valleys that trick the network into stopping early, you list these exact fixes. Swap to a ReLU activation to stop vanishing gradients. Stabilize your inputs with batch normalization. Ensure proper initialization of your weights to kickstart convergence speed. And finally, use gradient clipping to literally cap those exploding gradients before they blow up and cause an overflow. And just like that, we've reached the final stage of our explainer, Section 6, Rapid Exam Revision. This is designed to lock this material right into your short-term memory just before you take that test. These are your high-yield foundational takeaways that bridge Unit 1's architecture with Unit 2's optimization mechanics. First, remember the neuron components: inputs, weights, bias, and activation. Second, remember that ReLU is vastly superior to Sigmoid for deep layers because it prevents vanishing gradients. Third, drill that 4-step learning process into your head: forward, error, backprop, update. Fourth, know the clear trade-offs of batch's stability versus SGD's speed. And finally, remember that the ADAM optimizer is the ultimate hybrid for super efficient training. You've just speed-run the core mechanics of deep learning. You understand the structures, you get the math, and you know the optimizations. You now have the conceptual blueprint. So go into that exam room with absolute confidence. But hey, as you're filling out your test, ask yourself, if these relatively simple mathematical loops can already recognize voices and drive cars today, what on earth happens when we scale them up by 1 trillion? The midterm is really just the beginning. Good luck on the exam, and I'll see you next time.